Hello. In this video, we will discuss triple integration through an example. And the example says, calculate the volume of a cone of radius A and height h. Let's draw a cone, a general cone. This is a cone of height h and radius A. And I chose the cone so that the tip of the cone is at the origin of my coordinate system, where you can see the x-axis is going out of the screen, the y-axis is to the right, and the z-axis is going up. Now, as you can see, the z-axis goes through the center. It's the center axis of the cone, and the cone is symmetric around the z-axis, which means that if you rotate the z-axis, if you rotate the cone around the z-axis, then the cone will keep its shape. It's symmetric. Now, what is the equation of the cone? The surface of the cone is given by the following equation. In general, cones are given by the equation that z is equal to the square root of x squared plus y squared. And that square root is multiplied by some constant that depends on the height and radius of the cone. In our example, you can see that it is h divided by a. Now let's try to prove that, or not prove that, but at least to see that it is a correct formula. You can see that at the origin, when x and y are zeros, so z also will be zero. And that means the cone will be touching or be at the origin. Now, as z goes up or increases, and let's say we fix z, so when z is constant, we will get the equation of a circle. And that's, as you can see, the cone is really, when you cut it horizontally, you get cross-sectional areas of discs. So it's a circle shape. Now, when x and y, or when we reach the maximum height of the cone, we will get the base of the cone, which has radius a. So at that height, x squared plus y squared will be the radius a squared. And if you substitute x squared plus y squared equal to a squared, and then you take the square root, it will cancel the a, and you get z equal to h. That's the height of the cone. So this is the correct equation for the cone. Now we're going to start working on the triple integration. In general, let me write the triple integration, which will give us the volume. So I'm going to have triple integration of what? Well, then that depends on your choice of coordinates. In general, we have three famous coordinate systems that we can use. We can do the calculation in Cartesian coordinates, or we can use spherical coordinates, or we can use cylindrical coordinates. There are other systems also, but those are the three famous ones. Now, which one will we use? Well, that depends on the problem and on the difficulty and on your choice. Once I see a cone which has circular cross sections, I wouldn't think about using the Cartesian system, as I know that it's not really a suitable system to use. I will be thinking about either cylindrical system or spherical system. Now, which one would I use? That would depend also on which one is easier and which one you prefer and which one is more suitable to this problem. Let's say I don't know which one is easier to use, so I can try both, and then I can check which one I will find it to be much easier to use. That will come with experience. And it's a good idea that you can try all the different systems and you can check each one and see the difficulty in each choice. So let's say we decided to solve the problem in cylindrical coordinates. Now, what's going to be inside the integral? In cylindrical coordinates, the small element of volume is r dr d theta dz. So I know that this is the volume element, a small volume, infinitesimal volume in cylindrical coordinates. Once I decided on the coordinate system, I know exactly what to put inside the integral. The only problem now is how to write the boundary limits, the limits of integrations. And that is the main task of the problem. So let's do that in the next step. Okay, so now we want to discuss how to write the limits of the integration. Now this again will depend on which order of integration are we going to start with. Will we start integrating over r and then theta and finally z, or maybe start with z and then the other two, and so on. So there is a choice here on the order of integration. Now, which order should I use? Again, that's be a matter of choice for you. It could depend on the problem itself. One order may be easy, another order may be more difficult. So you have to decide on what is the suitable order that you should follow. In many examples, any order will work. However, in other exercises, problems, you will find out that one order is most suitable than the other choices. So let's go back to our problem. And now let's try to decide on which order to use. Let's say I don't know which order I want to, or which one is easier. So we can try any order of them and check. Let me start with taking first the order of z. So I'm going to integrate over z first and then think about the other two parameters or variables. So let's say I'm going to keep r dr d theta and just concentrate on the integration of dz. Now here I have to think now, what are the limits I should put for z? Now to do this, we have to imagine the shape. Let's go back to the shape now. And let's imagine that we are inside the cone and we are thinking about z direction up and down. So let's take a slice, a vertical slice of this cone. You can see that we will get triangle. This is a vertical triangle. It's a slice, a vertical slice of the cone. Now let's consider the z-axis. Let's say I am somewhere inside this slice and I am somewhere here. So now let's consider the z direction. So I'm gonna add pieces until I go up until I hit the top side of the slice. I'm gonna go down until I hit the bottom side of the cone or of the slice. I can go somewhere else just to check. Again, I'm gonna add pieces of z until I hit the top side. I'm gonna go down until I hit the bottom side. Anywhere you are inside the cone, you're gonna see that. You're gonna start from the lower side, which is the surface of the cone, to the top of side, which is the base, which is the circular base of the cone. So from this, I know the limits. So z gonna start from z equal, as we explained, h over a times the square root of x squared plus y squared. Of course, we're not using Cartesian, so I'm going to change that into polar, or into cylindrical. Now this is exactly r in cylindrical coordinates, which is the same as in polar coordinates. So I'm going to substitute and say that's r. So the lower limit of the integration over z will be from h over a times r until I hit the upper high. But you can see that the upper limit is just a fixed value of z, and that's the height of the cone. So that's z equal h. From this, I know the limits of integration for z from the lower side of that's the surface of the cone, to the top side, which is just the height of the cone. So now let's go back, and now I will put the limits of z from z equal h over a multiplied by the radius r, and then it will go up to h. This way I decided, or I found out the limits of integration for z. And you can see that the limits, at least the lower limit, is a function of r. Now let's decide on the other two limits for theta and for r. So now, to integrate over r, let me move d theta now. Let's just take d theta from here and just put it in here. So now let's concentrate on the integration over r, the limits of that. Well, let's go back to the slice that we did. Now, for this slice that I draw, this is the distance r. It's how far are you from the z-axis. So that's r. So now you ask yourself, what is the smallest value for r and what will be the maximum value for r? It's clear that the smallest value for r is 0, which means that this slice that I did is exactly on the z-axis. So r will be starting from 0, and it will go to the maximum value when I chose this slice here, which has r equal a. So r gonna start from 0, which means you are on the z-axis, and it will go to the maximum possible value, which is radius a. So if you go back now to the integration over r, I'm gonna say r gonna start from 0, and it will go to the maximum value, which is a. Now, once you do those two pieces, the integration over z and integration over r, you are really integrating over that small, the right hand or the right side triangle. Let's go back to this. So you are integrating over this area. Now, when you integrate over theta, you're gonna take all the values of theta, which gonna rotate this piece around the z-axis by 2 pi, by an angle of 360 degrees, which gonna then fill the whole cone. So the integration over theta is very simple. Theta is gonna be changing from 0 to a complete round of 2 pi. So these are the limits of integrations. Given that the order is, I'm gonna start first by integrating over z, then I'm gonna integrate over r, and finally with theta. Of course, the integration over theta has nothing to do, as you can see, with the integration over r and dz. So I could even do it from the beginning. The integration over theta is gonna give me 2 pi. And that's it. Now for the other two, I have to be careful about the order. I'm gonna start with dz first. Now the integration of dz gonna be z. The limits from the lower limit to the upper limit. So I'm gonna keep the integration over r for now. I'm gonna just do the integration over z and substitute the limits, and the limits will give me h minus h over a times r. And r, the limits are, as we said, from 0 to a. Now I have to be careful, because once we substitute the limits over z, we have r in the bracket. So that will be part of our final integration. Now we're going to do this simple integration, and the answer is going to be, I got 2 pi from here. Now integrating over r will give us the first term will be h, and then r dr is r square over 2. If you put the limits from 0 to a, you're going to get a square over 2. The last term, I got h over a, and then there's r, but there's another r outside the bracket, so that's r squared dr. Integration will give us r cubed over 3. Substituting the limits will give us a cube over 3. Let's just simplify the answer. The answer will be 2 pi. I have h outside. I get a squared. You can see this will simplify to a squared. So I get a squared. And then I get half minus 1 over 3. And that will give us 1 over 6. Simplify for the last time. Gonna get pi a squared h over 3. And that's the famous formula for the volume of a cone. So here we found the volume of a cone using triple integration for a specific choice of order. We ordered over z, then r. I could stop here, but I would ask the following question myself and you. What if we change the order? And let's say I don't want to start with integrating over z, but I'm going to start integrating over r. What's the difference? So that will be the final step in this example before we leave. So let's think about changing the order of the integration. So the volume is, and let's start with integration over r. So now we have r dr. Of course, here we have dz and we have d theta. So now I'm going to start with integrating over r. To do this, I'm going to cut the cone in a horizontal slice. That's at z height, which is constant. At a constant z, I'm going to get a disk. So this disk will have a radius r. Now, I'm taking pieces of this r. I'm going to add all of them to do the integration over r. So the question is, what are the limits? Now it's clear that the smallest value for r will be 0. So r going to start from 0. And then it will increase until I touch the upper of the curve of the circle. Now this circle is not the top, it's not the base, it's just a slice within the cone. And the equation of that circle is, we can get it from the equation of the cone. This is part of the cone. So it is z is equal h over a times r. From that, I know that r is a over h times z. So it depends on the height. Now, note that as we go up, as z increases, the radius will increase. As we go down, the radius will decrease. So now, the upper limit of r will be a over h times z. Now, to do the integration over z, it's going to be easy. That's going to be easy. The lowest value for z will be 0, and that's from the tip of the cone up to the largest value of z, which is h. For theta, it's going to just be the rotation over 2 pi. So these are the limits if I do the integration over r first. And the answer is going to be, integration over theta is simple. I'm going to do it first, 2 pi. I'm going to keep the integration over z for now and do the integration over r. The integration is simple, it's r squared over 2, and then I'm going to substitute the limits. So that will be a over h z squared divided by 2. So that's the integration over r, substituting the limits, and finally we can do the integration over z, which is a simple thing to do. So I got 2 pi, I got a over h already squared, divided by 2, and what is left inside is z squared dz, and the integration is simply h cubed over 3. Now let's simplify that. The answer is pi. I'm gonna get a squared and h squared down, h cubed up. I'm gonna be left with 1h divided by 3. So it's the same answer. So in this example, we calculated the volume of a cone using cylindrical coordinates and using 2 choices of ordering in the integration. I hope this video is clear. If you have any comments, any questions, please leave them in the comment down. Thank you very much for listening. See you in another video.